Hello and welcome to the second video of the FP1 chapter, Roots of Quadratic Equations. Start a question on the screen to review the previous work if you've got time. Pause the video now and give this a go. It's giving us alpha and beta, and we need to remember the relation alpha plus beta is equal to minus b over a in the quadratic equation, and alpha beta is equal to c over a. Then we just work this out. 4 over 3 plus 3 over 5. Change those to 15s, gives us 29 over 15, and that is minus b over a. Multiplying them, 4 over 5 is equal to c over a. So we can put this into the equation x squared plus b over ax plus c over a is equal to 0, which gives us a minus 29 over 15 here, plus 4 over 5 here, and then we need to make sure that they are integer values, so we just multiply everything by 15. And here is our answer. In this video, we're going to form quadratic equations with roots related to the roots we've got. And a lot of this work is going to be manipulating alphas and betas to give alpha plus beta and alpha times beta, like we did at the end of the previous video. So we've got this statement from the previous video. If the roots of the quadratic equation are alpha and beta, then we know these two relations that we just used in the starter question. We can create equations that have roots related to these two roots. And to do that, you need to be able to write the sum and the product of the new roots in terms of the sum and the product of the two roots that you know. That will be the majority of the work, and it might involve a fair bit of algebra. It also might get a bit confusing with the alphas and the betas, because the new alpha won't be written as a different symbol. It won't be alpha prime like I've written it here. It will be something related to the old alpha, maybe a 1 over alpha squared, or alpha plus beta over alpha, or something like that. So there will be some expressions here, and one of the difficulties is not to get confused with all the alphas and betas floating around. Once you've found the sum and product of the new roots, however those expressions look, you can then find the values of a, b, and c in the equation that you're trying to find by using these relations again. But at that point you'll be using the new alpha plus the new beta to give you the new minus b over a, the new alpha times the new beta to give you the new c over a, and then you can generate your new equation. And in terms of notes, that's it. So we're going to jump into two examples now. The roots of the quadratic equation this are alpha and beta. Form a quadratic equation with integer coefficients, don't forget to come back to this at the very end, which has roots alpha squared and beta squared. So this is the new alpha, the new root, which is the square of the old alpha. This is the new beta, which is the square of the old beta. So what we need to be able to find here is the sum of the new roots and the product of the new roots in terms of the old roots alpha plus beta and alpha times beta. To do that, we need to be able to manipulate these expressions in terms of those two things, and we'll be able to find these by looking at the old equation here and putting in the numbers here. So I'm going to start with the bottom one because this is a little bit easier. That's just alpha beta squared. And we know alpha beta because we can find that from the old equation. C over a. So that's minus 6 over 3 minus 2. So the product of the old roots is minus 2, and the product of the new roots is the product of the old roots squared. So that's 4. So that relates to the new equation c over a, the constant and coefficient of the new equation. I wouldn't normally write that all in one long line, but I wanted to show the progression there. Now we have to do the same thing with the top one, the sum of the new roots, we need to be able to find this in terms of the sum of the old roots and or the product of the old roots. And here again we see the use of the identity alpha plus beta all squared, because if you subtract 2 alpha beta from that, we get alpha squared plus beta squared. Now we need the sum of the old roots is minus b over a, so that's minus 1 over 3 from the old equation. And now we can substitute these two values. We've got minus 1 over 3 here. We need to square that. Minus 2 times the product of the old roots. And this will give us the sum of the new roots, 37 over 9. And that relates to the new equation as minus b over a. So these two statements are equivalent to these two statements, but with the new equation. So our new equation, we can now write it x squared plus b over a x plus c over a must be x squared minus 37 over 9x plus 4. And here we need to go back to integer coefficients. So we just need to multiply everything here by 9. We get 9x squared minus 37x plus 36 equals 0. So this is the equation that has roots alpha squared and beta squared, where the values of alpha and beta themselves are still the roots of the old equation here. So let me just clear that off and we'll go through the next one. 1 over alpha and 1 over beta. From this point on, for part B and also for both parts of the next example, it's basically exactly the same thing, just with a slightly different expression. So we've got 1 over alpha, 1 over beta. We need to find 1 over alpha plus 1 over beta, the sum of the new roots. And to do that, we need to be able to write it in terms of the sum and product of the old roots, because those are the things that we know. We still know alpha plus beta equals minus 1 over 3, and we still know alpha beta equals minus 2. To do this, we can add our fractions together. We get beta over alpha beta plus alpha over alpha beta is equal to alpha plus beta over alpha beta. Now that is equal to minus a third divided by minus 2, which gives us 1 over 6. Again, the product of these two is a little bit easier. And that is minus 1 over 2. So our new equation, we've got x squared minus the sum times x plus the product. And then again, put it into integer form. And this is the equation that has roots 1 over alpha and 1 over beta, where again alpha and beta themselves are still the roots of this equation. Next one, let's change up the equation. We've got 2x squared plus 5x minus 4. So the old roots, put in green up here, alpha plus beta is equal to a minus 5 over 2. Alpha beta is equal to minus 2. Part A, we've got the cubic that I referred to in the previous video. We're going to need to expand out alpha plus beta cubed in order to relate alpha cubed and beta cubed, but there's a whole bunch of stuff in between as well. We get 3 alpha squared beta and 3 alpha beta squared. So to manipulate this to get alpha cubed plus beta cubed, we need to realize that we can factorize out 3 alpha beta here, which leaves us with alpha plus beta, both things that we know. And then we can rearrange this to isolate the two that we want in terms of the things that we know. And there we go. Now we put in the numbers. we've got alpha plus beta is minus 5 over 2. We need to cube that. Minus 3 times alpha beta minus 2. And then alpha plus beta minus 5 over 2. And that will give us minus 125 over 8 minus 15. Minus 245 over 8. Now we also need alpha cubed, beta cubed, and again this is a little bit easier. Gives us minus 8. And then we put it into the new equation, so the sum is equal to minus 245 over 8, so we have to negate that, so that's a plus 245 over 8x minus 8 equals 0, and again integer coefficients, 8x squared plus 245x minus 64 equals 0. Final example, clear this off. This is still equal to minus 2, and this is still equal to minus 5 over 2. Now we want alpha plus beta over alpha squared, and alpha plus beta over beta squared, so we need to find the sum and the product of these two things. I said in the previous video, if you're not sure how to put it in terms of the things that you know with fractions, put them together first. That's usually a good first step. So to put these together, we're going to need beta squared alpha plus beta over alpha squared beta squared, and already that denominator is looking better, plus alpha squared alpha plus beta over alpha squared beta squared. Then if we combine our two, and we can factorize out a common bracket alpha plus beta. So writing this as one fraction, we've got alpha plus beta as a common factor, and that leaves beta squared plus alpha squared, and all of that is over alpha squared beta squared. Now the beta squared plus alpha squared, again we've seen this before a couple of times now, that can be rewritten as alpha plus beta all squared minus 2 alpha beta, and you can see it does get a bit messy when you're trying to do this, but if you persevere, so long as you can get the alpha beta and the alpha plus beta as your things, then you can put in, no matter how messy it gets, you can just put in the numbers when you're ready. So here we've got minus 5 over 2 times minus 5 over 2 squared minus 2 times minus 2, all divided by minus 2 squared. And I'm just going to drop all of that on my calculator, which gives minus 205 over 32. Then the product, alpha plus beta over alpha squared times alpha plus beta over beta squared, and we find yet again that this is a slightly easier manipulation. So we've got minus 5 over 2 squared divided by minus 2 squared, which is 25 over 16. So our equation, x squared plus 205 over 32x plus 25 over 16 equals 0, becomes, with integer coefficients, 32x squared plus 205x plus 50 equals 0. And there we go. Very similar process every time. The difficulty and the change from question to question is what manipulation and how complicated it is in order to find the sum of your two new roots in terms of your old roots, sum and product. And I hope that is enough now for you to have a go at the questions from exercise 2b for questions like those in this video, and then the Chapter 2 review exercise to review all of this work in Chapter 2. And maybe I'll see you in Chapter 3.